Good day. This is Ryan L. and today we will learn analog mixed-signal behavioral modeling and approaches. This material provides discussion about analog and mixed-signal modeling and verification approaches at behavioral level. The presentation is divided into two major parts: analog mixed-signal behavioral modeling, when to use what, and analog and mixed-signal modeling approaches. The first part discusses the mixed-signal verification dilemma and how do we know the models are good. While the latter discusses challenges in AMS design and modeling, analog and mixed-signal modeling approaches and performance trade-off. Part 1: Analog mixed-signal behavioral modeling, when to use what. Mixed-signal verification is a tough challenge, and much of the difficulty lies with models. How can engineers choose the right modeling approach and guarantee that models accurately represent the silicon? The mixed-signal verification dilemma. What mixed-signal designers really want is fast and accurate simulation of a full chip with the package. But SPICE can take weeks to finish, and digital simulation is fast but doesn't consider analog effects. You can run a small block on SPICE, but that doesn't tell you if the block works properly in the context of the chip. Behavioral modeling is the process of developing a model for a device or a system component representing the behavior rather than from a microscopic description. You can use behavioral modeling in the domain of analog simulation to model new device types and for black box modeling of complex systems. There are several styles of behavioral modeling that can apply to mixed-signal designs. The identified three are supported by the Cadence Virtuoso AMS Designer. Conservative models with Verilog A or Verilog AMS. This approach uses an analog kernel, evaluates voltage and current, and solves Kirchhoff's equations. Models can be integrated into a full analog simulation. But, you could represent a band gap with hundreds of transistors with a few lines of code. Signal flow models. Equations are easy to solve, but the signal flow is unidirectional. Models provide input-output feedback but no loading. This is useful for abstract analog models. Event-driven models. Here, code is evaluated only at events. Simulation time grows linearly with the number of events. This is useful for digital, mixed-signal, and high-level models. So when to use what? The conservative style provided by Verilog A and Verilog AMS is useful when there are significant accuracy requirements. This approach can potentially provide a 50 to 100 times speed-up over SPICE, but it all depends on how good your modeling is. If you're a poor modeler, there's a chance you could end up with a model that's as slow as SPICE simulation or even slower. Real number modeling, also available through Verilog AMS with the W-Real data type, brings real number values into event-driven digital simulation. It thus has the speed benefits of digital simulation and can leverage the metric-driven verification methodology that's increasingly used by digital engineers. It's good when there are hard performance requirements and limited accuracy requirements. For example, W-Real is very useful for full-chip mixed-signal simulations. The following chart in Figure 1 shows the accuracy or speed trade-off ranges provided by various analog mixed-signal modeling alternatives. Note that the conservative modeling style has a broad possible range, depending on how good the modeling is. Also important is the modeling effort shown in Figure 2. Here we can see that conservative models require the most amount of effort. You can potentially spend days, weeks, months to develop good behavioral models. W-Real models are relatively fast to develop because they're less detailed. An important rule of thumb: model what you need, not what you can. How do we know the models are good? Behavioral models are worthless if they don't accurately represent the silicon. Continuous model validation is necessary because both designs and models change over time. One small change to a model or the design could invalidate the model. You can run through a demo of AMS-DMV, a Cadence Virtuoso model validation tool mainly targeted at analog mixed signal. It provides an automated way to quickly run regression tests, but it's not a replacement for an analog designer who can do a detailed model validation. Don't be scared it will replace your job. It doesn't know the details of the model or the circuitry, it just raises a flag if the simulation results are different from what they should be. Part 2 – Analog and Mixed Signal Modeling Approaches. This section provides an insight into various approaches followed for analog and mixed signal (AMS) modeling and the associated challenges. The emphasis is on analyzing various approaches and finally providing options that can be used right from architectural exploration to implementation with a co-simulation based approach. In today's world, AMS models are used for architecture exploration and performance evaluation. The AMS models are also used in place of mixed signal IPs for faster simulation in co-simulation environments. The conventional co-simulation approaches are time-consuming with respect to setup and execution. This section starts highlighting the challenges involved in AMS designing and modeling, and then different modeling techniques are explained in brief. Challenges in AMS design and modeling. Design stability in AMS systems is achieved after the design is simulated across all the corners and at all process, voltage and temperature (PVT) conditions. Simulators which support AMS simulation are expensive and slow. In addition, co-simulation setup is a time-consuming process. Modeling AMS system involves trade-off between simulation time and accuracy. Simulink can capture continuous time behavior, but do not target the design of AMS systems at an architecture level. HDLs like VHDL-AMS and Verilog-AMS target the design of mixed-signal subsystems close to implementation level, but these languages have limited capabilities to provide efficient hardware-software co-design at high level of abstraction. There is a lack in offering seamless design refinement flow for mixed-signal discrete event, continuous time systems and hardware-software systems at architecture level. Analog and mixed signal modeling approaches. VHDL-AMS and Verilog-AMS allow modeling of discrete and continuous time signals or a combination of both. All aforesaid HDL languages can represent AMS systems at a higher level of abstraction by bringing down the simulation time while providing the intended functionality of the design. The following sections describe the process of modeling in each of the languages and finally a comparison of all the available modeling options to give a clear understanding of the pros and cons of each language. 1. VHDL-AMS. VHDL-AMS is an extension of VHDL to model AMS circuits and systems. Both electrical and non-electrical systems can be described at different levels of abstraction using VHDL-AMS. The VHDL-AMS cycle starts with initialization phase, which consists of the following main steps: computation of initial values of the driving signals, and quantities defined by attributes. Process execution until they are suspended. End of processes execution and setting simulation time to 0. Verilog A follows a similar initialization technique. The actual VHDL-AMS simulation cycle begins with the computation of analog solution points arrow 1 in Figure 3. This continues until the next digital event is scheduled or an event occurs on the analog and digital interface arrow 2 in Figure 3. To compute a digital evaluation point, signals are updated first. After that, any triggered processes are executed until they settle. If the time for the next digital evaluation Tn is equal to current time Tc, the digital simulator is called again, arrow 3 in figure 3. If Tn is not equal to Tc, the analog solver is called, and the next cycle begins, arrow 4 in figure 3. This continues until the end of simulation is reached, arrow 5 in figure 3. 2. Verilog A. Verilog A allows the designer to capture the behavior of AMS designs at different levels of abstraction. Figure 4 indicates the typical Verilog A simulation cycle. Initialization. The initialization phase of a transient analysis is the process of initializing the circuit state at time 0. Synchronization. A Verilog A simulation consists of a number of analog and digital processes communicating via events, shared memory and conservative nodes. All conservative nodes macro process are represented by matrices and solved jointly. Evaluation. The design description consists of differential and nonlinear equations which are discredited and solved iteratively. Update. Analog processes are sensitive to changes in all variables and digital signals read by the process unless that access is only in statements guarded by event expressions. Upon waking up, the process computes a new solution point, schedules its next wake-up event appropriately and then deactivates itself. Convergence. In analog kernel, the behavioral description is evaluated iteratively. On the first iteration, the signal values used in the expressions are approximate. As the iterations progress, the signal values approach the solution. Iterations continue until the difference between two consecutive solutions is less than an absolute tolerance value and the Kirchhoff's flow laws are satisfied. 3. MATLAB, Simulink. MATLAB Simulink or other interpretation tools can be used to model AMS systems if supporting libraries and functions are available. Simulink has an inbuilt analog tool set which can be used for AMS modeling and the accuracy results are comparable to that of SPICE simulation results. At higher levels of abstraction, this can be used for architectural exploration where the feasibility of a particular architecture and its functionality through simulations can be explored. The high cost of simulators, the increase in simulation time as the level of design abstraction reduces and problems with co-simulation make Simulink a non-preferred flow for AMS designs. The ideal model-based development design process is consisted of 6 components: defining the system, identifying system components, modeling the system with equations, building the Simulink block diagram, running the simulation, and validating the simulation results. 4. PSpice. Unlike Verilog A model which is HDL level, PSpice is device level. A SPICE model is a text description of a circuit component used by the SPICE simulator to mathematically predict the behavior of that part under varying conditions. SPICE models range from the simplest one-line descriptions of a passive component such as a resistor, to extremely complex sub-circuits that can be hundreds of lines long. PSpice AD is a simulation program that models the behavior of a circuit containing any mix of analog and digital devices. Used with ORCID capture for design entry, you can think of PSpice AD as a software-based breadboard of your circuit that you can use to test and refine your design before ever touching a piece of hardware. Because the analog and digital simulation algorithms are built into the same program, PSpice AD simulates mixed-signal circuits with no performance degradation because of tightly coupled feedback loops between the analog and digital sections. PSpice AD supports analog and digital behavioral modeling, so you can describe functional blocks of circuitry using mathematical expressions and functions. PSpice simulates analog-only, mixed analog, digital, and digital-only circuits. PSpice analog and digital algorithms are built into the same program so that mixed analog-digital circuits can be simulated with tightly coupled feedback loops between the analog and digital sections without any performance degradation. After you prepare a design for simulation, OrchidCapture generates a circuit file set. The circuit file set, containing the circuit netlist and analysis commands, is read by PSpice for simulation. PSpice formulates these into meaningful graphical plots, which you can mark for display directly from your schematic page using markers. Shown in Figure 6 is the process and data flow for the model editor. Modeling approaches and performance trade-off. The block diagram of different modeling approaches for AMS design is as shown in Figure 7. There are 4 options presented: Option 1, Verilog HDL, Option 2, Verilog A, Option 3, MATLAB, Simulink, and Option 4, PSpice. The choice of modeling language is relative to purpose and product application. MATLAB, Simulink, on the other hand, can perform HDL co-simulation and FPGA in the loop (FIL) simulation. Table 1 provides information about the comparison of various parameters for each of the approaches used for AMS systems. The main parameters considered are accuracy, abstraction level, time required for modeling the system, simulation times, tools required, and the support. Conclusion. The study of various modeling options available for AMS systems provided an opportunity to explore the different architectures with an emphasis on co-simulation and parameters like accuracy, time to model, simulation time, etc. It is recommended to use an appropriate approach based on the criticality of parameters and usage of application. You just have learned analog mixed signal behavioral modeling and approaches. Thank you very much.